Welcome to episode 10 in the series on differential geometry. In this episode, we will discuss Frenet formulas. First, let's define some vector fields relevant to curves in R3. If beta is a unit speed curve, we'll define the unit tangent vector field to be the vector field beta prime. We'll denote that T. The curvature of beta is defined as the magnitude of the derivative of the unit tangent vector. This is denoted kappa. The principal normal vector is denoted n, and this is equal to the derivative of the unit tangent vector normalized by its magnitude, which is the curvature. The binormal vector field is denoted b, and it's just the cross product of t and n. So the unit tangent and the normal. The torsion of a curve is defined the negative of the binormal's derivative over the principal normal vector, and this is denoted tau. Next, let's consider a lemma, which is to the statement that these three vector fields, the unit tangent, the principal normal, and the binormal, form a basis of the tangent space. In other words, these three vector fields are all unit vector fields and are mutually orthogonal at each point. By way of terminology, this basis of the tangent space, if you will, or a frame field, is called the Frenet frame field on the curve beta. Let's check then that these are all unit vectors and mutually orthogonal. By definition, the unit tangent vector field is of unit length because beta is a unit speed curve. Since kappa is the magnitude of the derivative of t, it follows that the magnitude of the normal, which is 1 over kappa times the derivative, the magnitude of the derivative of t is just 1. By our earlier lemma, the magnitude of a cross product is the product of the vector's magnitudes times the sine of the angle between the vectors. Here, we should hope that the angle between t and n is 90 degrees, and indeed, since the dot product of the unit tangent with itself is 1, the derivative by the product rule is 2 times t prime dot t, but by the definition of the normal, which is constant multiple of t prime, we have that the normal dotted with the unit tangent vector is just 0. So indeed the angle between these two vectors is 90 degrees, and so the magnitude of the binormal vector is the magnitude of t times the magnitude of n times sine of theta. Sine of theta is 1, so the magnitude is just 1 times 1 times 1. Here we've also shown that n and t are orthogonal because their dot product is 0. Additionally, b, the binormal, is orthogonal to both n and t because it's the cross product of both n and t. So this was shown earlier, and we're just observing that it immediately imports the claim that we want, that B, N, and T are mutually orthogonal. So now we have a frame field given by these three different vector fields, and that is the Frenet frame field that we will refer to over and over again. Now we have a theorem which gives us these Frenet formulas. The Frenet formulas are ordinary differential equations that we have built into the way that the Frenet frame field has been defined. So given a unit speed curve beta with positive curvature and torsion tau, then the Frenet formulas are T prime equals kappa n, n prime equals negative kappa t plus tau b, and b prime equals negative tau n, which are pretty simple to look at, but they turn out to be very convenient. To prove that these formulas actually hold in general, the first and third we can accept immediately, since they are essential facts about the definitions of kappa and tau, in fact. So that those constants are being defined in terms of these formulas, so we don't need to prove those. What we do need to prove is the second. So what we might start with is writing the derivative of the normal in the Frenet basis. So the derivative must be a linear combination of t, n, and b, and the coefficients will be the dot products of n prime with these different basis vectors. So that's the first line in this alignment of equations. We can check that each of these dot products can be rewritten. So for example, n prime dot t is negative n dot t prime. The reason for that is the derivative of n dot t is 0. But by the product rule that we have for dot products, n prime dot t plus n dot t prime equals 0. That just means that we can, in summary, we can shift the prime from one constituent of the product to the other, and then take the negative. That's all we're doing in each of these examples, each of these terms. Then we use the definitions of curvature kappa and torsion tau to replace t prime and b prime with kappa n and negative tau n, respectively. And then we use the fact that since n is a unit vector, its dot product with itself is just 1. So we've simplified the expression we started with, and we have the second Frenet formula. Next, we prove this corollary, that given a unit speed curve beta with positive curvature, beta is a plane curve if and only if its torsion tau is equal to 0. To prove this claim, we'll suppose first that beta is a plane curve. Then there exist points P and Q such that beta of S minus P dotted with Q is equal to 0 for all S. This should look familiar. We would say that we could describe a plane as being the set of vectors which are perpendicular to a given normal vector. In this case, Q is serving the role of that normal vector, and P is just the point that we're using to centralize the curve. So in some sense, you might imagine a picture where we're looking at the plane that's orthogonal to Q, and it contains the point P. By differentiating this equation that we've developed, we know that the term negative P dot Q will vanish under differentiation. So it must be that beta prime dot Q and beta double prime dot Q are both 0. Thus, Q is always orthogonal to both T and N. Well, the binormal B is also orthogonal to both T and N. So B must be in the direction of Q. Furthermore, B is a unit vector, so it's either Q divided by its magnitude, or it's the negative of that vector. That means B is constant, and so its derivative is 0. By the third Frenet formula, tau must be 0, since the derivative of B is 0. That wasn't too difficult. Let's do the converse. Suppose the torsion tau is 0. Then immediately we know the binormal's derivative is 0. So B is parallel at all points S and can be identified with the same point of R3. So we're saying the binormal vector is always pointing in the same direction. So we will let that vector be identified with a point in R3 using a natural isomorphism between the tangent space in R3 at a point and R3 itself. We want to show that beta lies in a plane through the point beta 0 and is orthogonal to B. So we'll define the function f of s, which is equal to beta of s minus beta of 0, and then dotted with B. Clearly, f of 0 is equal to 0. Now consider the derivative of f with respect to s, which is, of course, b prime dot b. But b prime is a constant multiple of t, and t dot b is 0. So not only is f of 0 equal to 0, but its derivative is always 0, which means that f is identically equal to 0, and so beta lies entirely in this plane described by the equation beta of s minus beta of 0 dot b equals 0.